Welcome back to ECE 441A, 541A. Homecoming, does that mean everyone goes home? Is that the idea? But hopefully you are now listening if you aren't present. But speaking of being present, the week of Veterans Day is going to be different. We won't have class on that Monday. That's Veterans Day. Wednesday, we will not have class in this room. I'm traveling, and Friday is your exam. So I will try to see about Tuesday before that Wednesday relative to office hours, squeezing that between Veterans Day and the travel day. But homework 6 and homework 7 will be before exam number 3. Homework 6 is due on the Friday before the exam on the 16th of November, and homework 7 is due the Wednesday before. And those will all be concerned with Root Locus sketching, and lab number 2 is finishing up essentially pole placement, or where do we locate poles in the complex plane. And maybe you're finding that your results aren't quite what you expected, but are we really adequately modeling maybe the physical system? The physical system maybe has more going on than what we have assumed in our model. We've assumed an ideal scenario. We've assumed an ideal pure two-pole system, and we haven't accounted for maybe everything that might be present. And one of the ideas behind lab number 2 is to get you to think about what's the difference, if there is a difference, between what I expected and what I'm measuring. How do you explain that, or maybe face that in the real world if you're doing some work and your experimental results are not quite matching what you expected? What are you going to tell your boss when you go in and start to try to justify the design that you've created or the work that you've done, and it's not quite matching what you thought it should be producing? So that's really what you need to be doing for lab number 2. At the end, I believe, I ask you for some ideas or suggestions on how do you explain this difference between what you expected and maybe what you measured. That's lab number 2, and I hope that that's due today is the deadline. A lot of dates here. Lab number 3 is due the last day of class. I know this seems like forever away, but it's right on us, and the third exam will be next very quickly. It will happen very quickly, and I want to make sure that everybody's clued in to these dates and this odd week that we will have preceding or during exam number 3. So we'll squeeze a lot in, and one of the things we want to squeeze concerns the root locus and how do we draw these root locus diagrams. And today we will probably, the goal is to get 3, 4, 5, and 6. We probably won't get that far. We may get into goal number 5, but we'll shoot for 3, 4, 5, and 6 for construction rules. And here they are. Number 1 is, where do we start these root locus branches and where do we stop them, or where do they end? If they do end, some go off to infinity. And they don't end, but they obviously end on your page. But theoretically, those are going off in some infinite direction in the complex S-plane. Those that do terminate on open loop zeros, and I hope we are clear on what that means. Those are the roots of this polynomial that we've defined as little n of S. The zeros of that are our open loop zeros. The root locus branches start on our open loop poles, which are the roots of the denominator polynomial d of S in our generic or in our standard root locus structure. Number 2, rule number 2 is counting. Essentially, how many poles and zeros are to the right of a particular section of our French bread. No, of the segment of the real axis. We've split or segmented our real axis according to where the poles and zeros are on the real axis, and we want to now identify which pieces of the real line belong to the root locus. And it's all based on the phase angle condition. And if we have negative feedback, that's where this odd number of poles and zeros to the right comes from. And I've tried to give a couple of examples. If, for example, in the first one on the left, we have a single pole, then the root locus is everything to the left of that single pole. And the reason that's true is if you are standing anywhere on the left of that pole on the real line, what's the angle that that pole makes to get to you? Maybe it's better to stand at the pole and look and try to find where you are. What angle do you turn through to see that segment of the real line? You turn through an angle of 180 degrees. And every point on the root locus needs to have an angle of 180 degrees. And every point to the left of that single pole, if you look from that point, or I'm sorry, from the pole to that point, you will have 180 degrees or traveled through 180 degrees. Counter to that, the diagram on the right that has two poles, hopefully you can believe that the line segment between them has an angle of 180, but the reason why we don't have a root locus to the left of those two, or an even number, is because each of those poles are contributing 180 degrees. So you add 180 degrees and another 180 degrees, now you're up to 360 degrees, and the last time I checked, 360 did not equal 180. And we need all of the angles from these poles and zeros, when they all are added up algebraically, to equal minus 180 degrees for a point in the entire complex S-plane to belong to our root locus. And the only points on the real line that belong to the root locus are those points between those two poles, irrespective really of where they are located. One could be at minus 1/2, another one could be at minus 20. We still have that segment between them on the root locus. That needs to be second nature to you as you're going through this construction of the root locus. Number 3 is the asymptotic behavior. We're trying to draw straight lines that are guides or asymptotes to the way that our root locus branches behave, and those are given by some odd multiple of this fundamental angle. The fundamental angle is 180 divided by the pole zero excess, or P minus C. And where we locate those angles from the centroid is based on the sum of the poles minus the sum of the zeros divided by that pole zero excess. We will talk today about breakaway and reentry points on the real axis. Do we have such behavior on our line segments of the root locus? And that is based on trying to find relative maximums of K and relative minimums of K. And we can find that, we could even find that numerically. If you plugged in different values of S in this expression for K, which is this ratio of the magnitude of our denominator factors divided by the magnitude of the numerator factors, you could plug in real values of S where you know your root locus belongs and look for relative mins and relative maxes of K. You could plot that picture of K and say, oh, there's a relative max. Well, then I must have a breakaway. Oh, there's a relative min. Oh, I must have a reentry on the real axis. That's rule number 4. The imaginary axis crossing, again, all of these branches of our root locus, if they are a part of, if that point in the complex plane is a part of the root locus, it satisfies the magnitude condition and the phase condition. So if somebody just wants to iteratively figure it out. They can walk up the imaginary axis and say, what's the angle at this point, contributed by all the poles and zeros. If the angle is minus 180, then that point is a part of the root locus, and that's where the root locus branches cross the imaginary axis. That's the brute force way of finding omega sub c. Does it exist? Walk up the imaginary axis, not maybe literally, but in your mind, and evaluate angles at particular points. And if you're expecting the imaginary axis or the root locus to cross the imaginary axis, then at the crossing you should have a phase of minus 180 degrees. Again, this 180 degree condition allows us to figure out Rule 6, which are the angles of arrival and angles of departure from complex zeros and complex pole pairs. How do these branches arrive at their destination, which are these finite zeros? Do they come in at an angle of 45 degrees? Do they come in at an angle of 180 degrees? How are they approaching these complex zeros? Likewise, how do the branches exit or depart from these complex poles? Do they do they move away from these poles at an angle of 60 degrees? Do they move away at an angle of 90 degrees? That's all going to be rule number 6. So let's refresh with rule number 3, asymptotic behavior for large K. In this progression of rules, 1, 2, I think we have that, where those are pretty straightforward. 1, we know where we're starting, we know where we're ending, and 2, we're simply counting. 3 is the asymptotic behavior, and here is the way that I like to think of phi sub a. Usually I just focus on this fundamental angle, 180 divided by the pole zero excess. I can count the number of poles, I can count the number of zeros, finite zeros. That gives me a pole zero excess number, and I divide that into 180. That's my fundamental angle. So if that's 90 degrees, if it's 60 degrees, if it's 45 degrees, that's where my initial or fundamental angle begins, and then I just have to worry about odd multiples of that fundamental angle, where P in this equation corresponds to the number of poles of GH, and Z is the number of finite zeros of GH. And those angles, you have to pin them somewhere. Now we're at the birthday party and somebody's playing pin the asymptotes on the S-plane instead of pin the tail on the donkey. We've graduated, we've gone up, so the next birthday party you guys might have, you might play this game. Pin the asymptotes on the S-plane. Well, now the only place really that you're worrying about is the real line, and now that's an infinite in extent, so there's all sorts of options. But now you're saying, where is that collection of angles centered? What's their centroid? And you can find it by summing the poles minus the sum of the zeros divided by this common number P minus C, the pole zero excess. So let's do that for example number 2. First, we need to put in our X's and O's. And it's a good thing we can do X's and O's because it helps us win. Sorry. But we had a good weekend, right? Where do we put X's and O's in this diagram? Do we have any O's or open circles? Do we have any finite zeros? We do. We have 1 at minus 1. And then we have 3 poles, a pole at minus 4, a pole at minus 6, and a pole at minus 10. That's pretty easy. Now we can change colors and say, okay, which piece or which of these line segments belong to the root locus? Does the root locus belong to the right of that 0? If I stood at that 0, what's the 0's angle if I look to the right? If I look to the origin, what's the angle from that 0 to the origin? Do I have to move? I'm dead on. That's 0 degrees. 0 for all of those, so you sum up all of their angles and you have 0 degrees. That's not going to be a part of the root locus. But now if I'm... Oh, now you're going to see all my email. Better not do that. All 100,000 emails. Haven't emptied my inbox for a while. All right, but now we have this line segment between -4 and -1. That's a part of the root locus. We also, and that you can find by looking, and there's an odd number of poles and zeros to the right. There's nothing between -4 and -6, and there's something between -6 and -10, and nothing beyond -10. So now we have the segments that belong to the root locus. What we want to do is figure out what's going on. Well, we're leaving these poles, so we can draw arrows indicating the movement away from those poles, and now we have to figure out what's happening beyond that. And rule number 3 now tells us how we can figure out what these branches, how many branches of the root locus do we have in this example? How many root locus branches do we have? How many lines do you see on the page? 2. Is that how many branches we have? No, we have 3 branches. I've indicated branches by arrowheads, essentially. We had 3 open loop poles. We have 3 branches. 2 branches are actually on the same line segment from -6 to -10, and they can't stay there forever. And what happens off the real line can be figured out by looking at the pole zero excess. What is our pole zero excess in this case? How many poles do we have? 3 minus 1 finite 0. Our pole zero excess is 2. This now allows us to figure out what our asymptote angles will be and where they will be. Well, then we'll figure out where they're centered based on the poles and zeros. Phi sub A is now 180 degrees divided by pole zero excess of 2, and then we have odd multiples. That's really just 90 degrees. And how many L's do we have? L equals 0. That's our fundamental angle. And then we keep going up with L until P minus Z minus 1, 2 minus 1, or L equal to 1. So that now if we plug that L value in here, we have 90 for L equals 0, and we have 270 degrees for L equal 1. Or you might see me just say that's plus and minus 90 degrees for these asymptotes. And where are those asymptotes centered? That's the centroid. We have to now add up the poles. We had a pole at -4, one at -6, and one at -10. We add their locations. We subtract the locations of the zeros, which we have 1 of those, and we divide by the pole zero excess. We have 19 minus 19 divided by 2, or our centroid is at minus 9.5. So now we can come back to our diagram and say, oh, sigma sub A, which is the center, that's where we've pinned these angles. That's at minus 9.5, and now we know where our guidelines are for the root locus. That means that the branch coming from -6 and the branch coming from -10 are going to somehow meet between them and break away and eventually then approach. One's going to go here and one's going to go here. And what we need to do is figure out, where do they break away? Do they break away there? Where do they break away or exit the real line? And that's rule number 4. So let's now look at rule number 4 to help us figure out how to continue drawing this root locus sketch. In this particular example, we really only have breakaways. We don't have branches coming back into the real line, but the label on rule number 4 is breakaway and reentry on the real axis. And here's the description. Breakaway, and just if you're interested in reentry, that's going to be in parentheses. Breakaway points occur at relative maximums and the reentry occur at relative mins. Of our expression or our function that k is going to be defined by. Here's the example. And k is determined using one of our two conditions. We have the magnitude condition that has to be satisfied, and we have our phase condition which has to be satisfied. The magnitude condition says that we now have k, g of s, h of s, the magnitude of that equal to 1. And in our particular case, we know what g and h represent. We had a 0 factor and we had 3 poles. And that expression for different values of s, complex values of s, that are on the root locus needs to be true. Well, we can now solve this for k. If we solve this for k, now we can look at the magnitude of the complex number associated with the factor s plus 4 at whatever point s we select. S plus 6 will produce a number, and s plus 10 will produce a number, and we'll divide that by the complex number's magnitude associated with the s plus 1, or the 0 factor. Is it clear how I came up with this expression? Here's my function of k, and now I'm looking at particular values of s that cause this to be a relative maximum or a relative minimum. If we're looking for breakaway points, which we are in this particular example, we're looking for breakaway points, and between what values of s are we expecting a breakaway? Where do we expect the root locus branches to break away from the real line and approach the asymptotes? -6 and -10. Somewhere in that region, we are expecting a relative maximum. So we could sit down with a cup of coffee or whatever you enjoy. Well, no, maybe not. So a cup of coffee, and evaluate this for different values of s. And we know that we want to look at this we want to check points between s equal minus 6 and s equal minus 10. And you could now simply create a table of numbers. And here it could be just guess and solve for k and see where am I observing a relative maximum for k based on what value of s I put in. If I evaluate that expression at minus 6, what's k going to be? If I plug in minus 6 for s in that k expression, what pops out? 0, because that was actually a pole. And the gain is 0 at the poles, at the open loop poles. Likewise for minus 10. So on those two endpoints of my interval in question, I know that I'm starting at k equals 0. So now I'm hoping to find the relative maximum between those two 0 values. What if I now just said, well, I'm not going to really think too much. Let me just start plugging in some numbers. Minus 7. So if you evaluate this at minus 7, it's now pretty easy to calculate. You wouldn't even have to have your calculator. You could maybe even do this manually. And now you have 9 over 6, or 1.5 for k. Again, we're taking the magnitudes of these, so these will be positive values for the gain k. And k, remember what that is? That's this knob that we're adjusting from 0 to infinity. And as we turn it and get it bigger, that's going to move these closed loop poles on around in the s-plane, and their movement is restricted to being on the root locus diagram. Now we've seen that at minus 7 we have k equal to 9/6. If we now say minus 8, this maybe is a little bit different, but it ends up being 16 over 7. And that's now bigger than 2. And if we said, well, I don't know, have we reached a maximum yet? What's minus 9? S equal to minus 9. Well, that's now 15 over 8. Now we've gone from 1.5 to a little bit bigger than 2, and now we're less than 2. So we've experienced a relative maximum of k somewhere around minus 8. Is that clear? So if you iterated a little bit more, if you had a big cup of coffee, maybe you decide to go to 4 significant digits. And on an exam, no. Two-digit accuracy is acceptable. Minus 8.2, wow, that's pretty good. Because how are we going to, well, if you did that, if you evaluated this, you would get 2.31 for our relative max. And now we know a little bit more accurately where this root locus diagram, the two branches between minus 6 and minus 10, where they come together and separate. They break away at minus 8.2. That's why I say, okay, it's not necessary to get that accurate because you're drawing this on a piece of paper, and what's it going to, how accurate can you be? But here's 8.2, and now we go there and we go here, where these branches, and these are going to be smooth branches. If you wanted to, you could actually pull out a calculator if you happen to have one that sketched things. You could maybe even, don't get this confused, this is not the root locus diagram, this is the magnitude of k. But if this was now minus 10, this is our s, and this is minus 6. We know that the curve is 0 at minus 6 and minus 10, and now it just does something like this. And what we found is right here at minus 8.2 is where we have this peak of 2.31 for k. And that's a relative max. And if you wanted to do that on your calculator, maybe you would say, oh, k is the absolute of x plus 4 if x is a easier variable to find on your calculator. And now you could simply sketch that as a function of x between minus 6 and minus 10 and see where this function is maximized. Is it clear how we're using rule number 4, breakaway and reentry? If we were looking for a reentry, then we would look along a segment and try to find where does that k experience a relative minimum. And that's where the branches would reenter the real line between, let's say, 2 poles or a 0 and a pole, etc. That's rule number 4. Let's now look at rule number 5. Rule number 5 concerns imaginary axis crossing. Do the branches of our root locus go across the imaginary axis? In this example, would you expect an imaginary axis crossing? Would you expect to have to invoke rule number 5? No, there's no branches crossing the imaginary axis. Now, what does this actually tell us in this example? What values of k will stabilize this system? If somebody now put this system together and they had this knob k and they could adjust it from 0 to infinity, what restrictions do they have on that adjustment of k? You can crank k up as much as you want. As you crank it up, what's going to happen? Which of these behaviors, so as you crank up the gain k, let's say that you crank up the gain until you get to, let's say, a pole there and a pole here, and you would have its conjugate there. That triangle close to minus 1 is being kind of annihilated by that 0. It will have a little bit of an effect, but the majority of your behavior is actually going to be determined by those 2 poles that are complex conjugates. And as you crank up the gain k, what's your percent overshoot going to be relative to those triangles that are complex? As you crank up the gain k, what do you expect your percent overshoot to do? Get very big, huh? And what do you expect your settling time to do? If you keep cranking up the k, are you going to keep speeding up your system's settling time or shortening the settling time dramatically? How's the real part of those triangles, how is it moving as we crank up the gain k? Is it moving all the way over into the left half plane and getting bigger and bigger in the negative direction? No, we're kind of stuck, aren't we? We're sort of stuck at a real part of minus 9.5. That's our asymptotes, and they're at 90 degrees. So that we aren't going to speed up the settling time much by increasing the gain k. We will make our overshoot and speed of response, the rise time, will be much shorter. But those are the kinds of questions that you can now address or think about with this root locus diagram. Rule number 5, we're going to have to look at a different example because it involves crossing the imaginary axis. So here is branches of the root locus cross the imaginary axis if the phase angle condition is satisfied at that point. This is where we're walking up the imaginary axis and looking and checking the angle at each of these points as we walk up the imaginary axis. Let's look at a different example. Suppose now we have the following g of s. Suppose we have g of s equaling 1 over s, s plus 3, s plus 6. And let's now start the process of sketching the root locus diagram for that g. And if we don't give you an h, you can assume h is 1. So here's our gh. And I can plot a pole at the origin, a pole at -3, and a pole at -6. And now I have 4 segments of the real axis. Which of those segments belong to the root locus? Does the segment from the origin to plus infinity belong on the root locus? Are there an odd number of poles and zeros to the right of any point in the right half plane? No. So now if I step anywhere here, I hope you can see that I have an odd number of poles and zeros to my right. The root locus won't be between -3 and -6, but it will be from -6 to -infinity. Now what do we do? This pole goes there, this one goes there, and this one goes there. Do we have to worry about anything else? Are we finished? How many branches of the root locus do we have? How many segments do we have? We have 2, but how many branches of the root locus do we have? 3. So we have 3 branches, and what's our pole 0 excess? 3 minus 0, that's 3. So we actually are going to have some asymptotic behavior at a fundamental angle of 180 divided by that pole 0 excess, or 180 divided by 3, or 60 degrees. So we have a fundamental angle of an asymptote at 60 degrees. Some of these branches are going to go off into the right half plane. If we crank up the gain k enough, we're going to go unstable. So let's now use rule number 3 to figure out a little bit more information to help us with our sketch. Phi sub a is 180 divided by this fundamental, or the pole 0 excess, which is 3, times, maybe I don't want to put that x there, you'll think that's a pole, 2l plus 1. L is now 0, 1, up to p minus z minus 1, or up to 2. So that now phi sub a, the fundamental angle, is 180 divided by 3, that's 60 degrees. That was with L equal to 0. And now we have odd multiples of that. 3 times 60 is 180. That was with L equal to 1. And then 60 times 5 is 300, or minus 60. And that's for L equal 2. There are asymptote angles. This was the p minus z minus 1 for our case. And what's sigma sub a? Where do we pin these angles on the real line? We have minus 0, that was the origin, minus 3, minus 6, minus, we didn't have any finite zeros, divided by 3 minus 0. We now have minus 9 divided by 3, or minus 3. That's actually at one of our poles, but that's a coincidence. That's not always going to happen. That's just because this example, I picked them to be very symmetric, 0, 3, and minus 6, and the root locus is actually a fairly symmetric diagram. But now we can draw these asymptote lines. The sigma sub A is right here, and we have our fundamental angle at 60 degrees. Here now you can go back and obtain your drawing tools from wherever you started doing drawing. Now you need your protractor and measure a 60 degree minus 60 degree. What do we need to do next? Those guidelines tell us how the branches will behave as k gets big. So this is now 60 degrees. This is 300 or minus 60 degrees, and we have one at 180, and that's the branch going off to minus infinity. How many branches do we have of the root locus? Keep harping on this, don't I? 3. 2 are going to go towards those angular, the angles that we see, and 1 is going off to minus infinity. We now need to figure out, okay, if the branch at the origin and the branch at minus 3, they're going to somehow meet, we're going to have a breakaway, and what do we expect, or what do we apply to find that breakaway? That's rule number 4. Based on the magnitude condition, which says that k times gh, that magnitude is equal to 1. In our particular example, that's what we have, and we can now solve that for k, and now we have this expression for k that we can start evaluating at different points. And if we did it numerically, we could again create this chart. And what's that chart going to say if we evaluate k at 0? That's going to be 0. At minus 3 it's 0. Okay, we're at least making sense with what we expected. What about at minus 1? First one's 1, the second one's 2. So now we have 2 times 5. That's going to give us a value of 10 for k. What about at minus 2? Now we have 2 from the first one, 1 from the middle one, and 4 from the other one. What did I just say? 2 times 1 times 4, 8. Well, okay, let's use our calculus. If we're looking for relative max, maybe I forgot my calculator. I can do this with my pencil and paper, right? So now what's this expression if I wanted to find it as a polynomial in S? That's going to be a cubic. Here we have s squared plus 9s plus 18, and I can now multiply that by s, and I have k equaling s cubed plus 9s squared plus 18s. Is that okay? Now, to find the relative max of that expression, I can differentiate with respect to s. I'm trying to find where is that k maximized in this region of s between 0 and minus 3. Let's see if the calculus will help us. These are polynomials. Don't you wish your math exams just had polynomials when you were asked to differentiate? So now if we differentiate, I have 3s squared plus 18s plus 18. Well, I can factor out a 3 to make it a little easier, and now I have s squared plus 6s plus 6 equal to 0. That's a quadratic. I can do my quadratic formula and find the roots of that. And if I do that, I see that I have 1 is at minus 1.3 and 1 is at minus 4.7. Where's my breakaway? at both of those, at either of those. Sometimes you get a root that's not even in the region that you're interested in. We're interested at S values between 0 and -3. So we don't even have to worry about the root at -4.7. That doesn't even exist on our root locus. Here is now our relative max. And if we now evaluate k at that value, we find that we have a k of 10.4. So now we have in our diagram, if we come back here, now it's going to, I have to split this in thirds. So let's say that's -1 and -2. At -1.3, I have a relative max. So now let me say that that's there. And now that one goes up and approaches that asymptote. This one is symmetric, and it goes down and approaches that asymptote. And do you see that eventually we are going to have an imaginary axis crossing? And if you can sketch this somewhat carefully, you can sort of eyeball what that imaginary axis crossing might actually be, if this is drawn somewhat carefully. But what if I said, I want a closed loop pole at -1? How would I design such a closed loop system? Do you have any tools that will allow you to do that based on what we've already done? What gain value, k, do I pick to have a closed loop pole at -1? Is that even possible? Can I have a closed loop pole at -5 for this interconnected system? No, because it's not on the root locus. I can't have a closed loop pole at -4. So if your boss says, I want a closed loop pole at -4, you'll just have to go and explain that that's not possible with this present configuration of poles and zeros. If you want, I'm going to have to introduce some more poles and zeros to get a pole at -4. Here's the design question. Everybody always wants to do design, so here's the design. Find a k to yield a closed loop pole at s equal -1. Well, what were we doing here? What did we just do to find k equal to 10.4? We plugged in an s value of -1.3. Well, if I want a closed loop pole at -1, then I really want to figure out what is my gain going to be to give me a closed loop pole there, and then my other poles are going to be somewhere on those branches. But to obtain a k to get me to -1, do you see that I simply have to evaluate that k function when s is equal to -1, and that will be the k that I need to give me my closed loop pole at -1. My other two closed loop poles will be between -3 and -1.3, and somewhere to the left of -6. But now I can use this formula, k equal to the magnitude of s plus 3, and the magnitude of s plus 6. I can evaluate that at s equal to -1, and what's the k going to be? It's going to be 1, it's going to be 2, and it's going to be 5. Boy, that's a nice sweet number, isn't it? 10. So now we crank up the gain to 10, and boom, we have a closed loop pole at -1. What we now need to do, and maybe I'll let you do that with your coffee, is walk up the imaginary axis and figure out where exactly are those branches going to cross the imaginary axis. And do you see how we would find the gain to get us there? Once we know omega sub c, we could evaluate that k formula at j omega c, and our k is that value. We'll pick up at that point on Wednesday.